In these exercises, we'll use a virtual machine running Linux Ubuntu 22.04. The VM can run on any native OS like Windows, Linux, or Mac OS, and includes all apps we'll need for RVpga, except for project and simulator sources, which we'll download a bit later. Moving on. First, download the VM from either of these two links. Both download the same file. If we click the first one, a new window opens. Click Download and Download Anyway. It's a large file, over 12 GB, so it may take several minutes to download. I've already got it in my Downloads folder. Make sure it's fully downloaded. We can see it's 12 GB and a bit more, confirming it's complete. The next step is installing the virtual machine. I'm using VirtualBox in this case. In VirtualBox, import the virtual service. Find the machine and install it by following the default steps. I already have the machine installed and running. Next, we'll download the RVfpga project sources and simulator binaries. Do this from the virtual machine. Copy this link and paste it into a browser there. Now open Firefox in the VM, paste the URL and start the download. Click this button and download anyway. This file is much smaller than the VM and should only take seconds to download. In the VM's Downloads folder, find the file and move it to the home directory. Extract it there. This path is crucial as many simulator and source paths point here. Let's go through the steps to run a simulation in RVfpga pipeline. First, we'll open Visual Studio Code in the virtual machine. Then we'll open our project located in the master folder under Projects and Project RVfpga Pipeline. We'll simply select it and click Open. This opens the project. Here we can see all the project files and folders, including src with the program we'll simulate. It's a simple program where we'll analyze a series of instructions in a loop. Before the loop, we initialize some registers and set a control instruction for cycle-by-cycle execution. Note that this instruction doesn't affect the processor's architectural state, as it simply performs a logical operation between two registers and writes the result to register 0. Which stays at 0. Next, we open the platform.io.ini file, which includes the project configuration. It has a line pointing to the simulator binary we'll use, RVfpga pipeline, the Ubuntu version located in this directory. If the directory path isn't correct, we'd need to modify it to properly point to the simulator. To start the simulation, click the platform.io icon and select the RVfpga Bitbo pipeline option, which launches either the Bitbo or pipeline simulator, depending on what's specified in platform.io.ini. In this case, it'll launch the EH1 pipeline simulator and open a new window. In this window, clicking the +1 cycle button runs the code and stops at this instruction, specifically when it's in the decode stage. Alright, let's analyze the simulation. By clicking this button, we simulate a new cycle and can examine each cycle to see what's happening in the pipeline, including instructions at each stage and key values of signals from different stages and both paths. However, we'll quickly jump to cycle 26 to analyze the pipeline state. We usually avoid analyzing the first loop iteration with our target instructions, as some structures aren't fully trained yet, which could obscure what we want to study. For instance, the branch predictor or instruction cache might fail initially. Okay, in this cycle we have multiple loop iterations running. Specifically, we see the third execution in these stages, the fourth here and the fifth there. Starting with the last stage right back, we have the first multiplication. In the second path, there's a bubble due to a structural risk between these two multiplications. At decode, both try to access the single multiplier. The first progressed, while the second had to wait. Since the EH1 multiplier is pipelined, we can execute multiplications in consecutive cycles. In write back, this multiplication is writing to the register bank through the first port, indicating it wants to write data 6. The write is enabled, this signal is 1, and it's specified that the register to write to is X5, which corresponds to T. In the commit stage, we have the second multiplication and the loop index decreasing by 1. As we can see, both instructions have obtained their results and will write to the register bank in the next cycle. In X3, we have the end of the third iteration with a jump. Thanks to the share branch predictor included in the EH1 processor and enabled in this example, no stalls are needed as it correctly predicted the branch would be taken, so there's no pipeline stall. Both instructions have their results. The multiplication result is the same for all iterations. In the next stage, X2 shows the mul and addi instructions of the fourth iteration progressing and getting results. The ADDI result is already available, and X1 shows the end of this iteration and the start of the next one. Finally, in the vcode stage, we have the fifth iteration, the multiplication of T1 and the ADDI. Note that for ADDI, we're shown where the operands are being obtained from. The first is obtained by bypass due to a dependency between this T2 and the T2 calculated in this ADDI instruction. That's why the data is provided in advance from here to here as indicated. The second operand, -1, is obtained from the immediate value in the instruction. To stop the simulation, simply close this window and press Ctrl+C in the terminal several times. Next, we'll demonstrate generating a program execution trace and visualizing the waveform in GTK Wave. First, we open Visual Studio Code and the project we'll use, located in the master folder, Projects, Project RVfpga. We select and open it. We trust the authors, click Yes, and can view the program in the SRC folder. As we see, the program is very simple, just a loop with 3 arithmetic logic instructions and a jump that loops indefinitely. In the platform.io.ini config file, we're pointing to the RVfpga trace binary of the Ubuntu version at this path. As always, if the path differs, we'd need to modify it. To generate the trace, click the platform.io icon and select the Generate Trace task. We click it, the program compiles, and shortly after, we'll get a success message for trace generation. Next, we'll open the trace generated in GTK Wave. For this, we'll open a terminal. Then we'll navigate to the directory with the generated trace. First, the master's material, RVfpga master UCLM projects, RVfpga trace. Here's a peak show dir with a build dir, then Swearwolf Nexus inside. In this directory, we see a generated file called trace.vcd. We can open this with GTK by typing gtkwave trace.vcde. We can show core signals using a TCL script in the project, test.tcl. Clicking Open will display the signals selected in that file. IFUI0 einst, IFUI1 einst, and the X28 register. In other programs, we might want to analyze different signals. Remember, this simulator lets us access any internal signal of the processor. Once we have the signals in GTK Wave, we'll do a zoom fit to show the entire trace. If we go to any point in the simulation and zoom in, we can see the specific values of each signal. I0 shows the code for each instruction being fetched. I1 the code for the second path, and this signal shows the register content as it changes while instructions are executed over the cycles. It helps to view the disassembled code in Visual Studio Code. If we open PO Servos Nexus firmware.this, that's the disassembled code. In the main function's repeat loop, we see the 4 instructions being repeated. Looking at the trace, we can confirm these are the instruction codes being fetched throughout the cycles. Next, we'll run a simulation in RVfpga Bitbo. In Visual Studio Code, we open the project. It's in the master folder, Projects, Project, RVfpga Bitbo. SRC shows the code, which after initialization has an infinite loop reading switch states and displaying them on LEDs. When switches change, LEDs will update accordingly. To start, ensure the path to Bitbo simulator binary is correct, then click RVfpga Bitbo pipeline in platform.io. The Bitbo simulation is now running. We need to open the board in the browser. For this, run the Python server in the master and simulator folders. We have this directory, and we need to run the server. With this command, python 3-mhttp.server-directory, and the directory we're referring to, which is included in this directory. The Python server is now up and running. We then connect to localhost 8000/nexus-7.html in the browser. The board and simulated peripherals are now displayed. We connect to the board, click this button, and can see the program's behavior. As mentioned, each switch change will be shown on the LEDs. Next, we'll run a program on the Nexus A7 board. First, connect it to your computer via USB and power it on. In the VM, connect it by right-clicking this icon and selecting Digilant USB device. Open Visual Studio Code. We'll run the same code we used in the Bitbo simulator. This will confirm that the operation is identical. The project is open. Verify the bitstream pointer is correct. It's pre-configured here. Next, download the bit stream to the FPGA. Click Upload Bitstream in Platform I/O. If successful, you'll see this message and the 7-segment displays will flash, then show 0. To run the program, click on Run and Debug, then on the Start Debugging button. This launches LED switches clang code on the board, which reads switches and displays their status on LEDs. When you click, the code compiles and starts running. By default, the code stops at the main label. We can debug step by step, analyze registers, memory, and also run the code continuously. So now each time we change a switch, the LED states will update. For our final test, we'll run the Whisper simulator in the virtual machine. We open the RVfpga pipeline project already open here. Note in platformio dot in I, we've set debug tool to Whisper. This will simulate the execution in this simulator. To launch, go to Run and Debug and click the green Start Debugging button. As I mentioned, the app will start running in this Whisper simulator. It might take a moment to start. The simulation stops at the main label. From there we can step through, continue execution, step into, even go backwards, and then analyze variables, registers, and other elements.